Thanks everyone for showing up despite the country facing its biggest crisis in recent memory, the rain, of course. I will indeed speak about an emerging field of research that we are trying to push in the last few years, which is using cryptography and other formal provable methods to guarantee things related to AI security. Okay, so something that I think I don't need to convince anyone in this room of is that modern machine learning works very well. It is very useful for many things. The other thing that most of you probably know very well is that we aren't really sure why. So we don't have any proofs or any theorems telling us when would training work or when can we trust a model. And something that, at least from the viewpoint of a mathematician, is a much larger sin than not having proofs, is that we do not even have definitions. So we don't know even very basic things. What does it mean to be a good language model? We have no agreed upon definition that everyone agrees with, which also means that it is very hard to argue about those things. On the other hand, if I want to contrast this to what we have with more classical types of security, in modern cryptography, we do have a system of proving that things are secure. So still, we have a small set of assumptions that are very widely believed and long-held and are very easy to state. But when we want to argue nowadays that some encryption is secure or that your bank account is secure, we can no longer say, I'm a bank, I ran some empirical tests in my basement, and I think that your bank account will be secure. We are not allowed to do that. So we need to have some form of a proof saying that if you would break the security, then something really bad would happen. This assumption would break. And the reason we are doing that is that we tried. We tried for many, many years. We have thousands of years of documented use of cryptography, of encryption, since the early Egyptians and after World War II, in which people did try to have empirical, proprietary systems of encryption and of cryptography, and those things failed miserably. So this is the reason we switched to this more formal form of modern cryptography. And now the main question is, can we also do that in machine learning? And what is the problem with attempting to do that for machine learning? The problem is, how could we think of adding formal security guarantees when even the task itself is not formally defined? How can I say that this is a good language model that also has some safety property if I cannot even prove that this language model is good in whichever utility definition I don't have? And this meant that when people tried to think of such problems before, they had to choose one of two roads. One road that people were choosing is what I mentioned before, saying, okay, so I am going to base my security and utility empirically. So I will run some benchmarks. I will run some competitions to see if people manage to find the backdoors and so on. And the other road that people have taken was, at least from the academic point of view, was to revert to archaic, old, not very useful forms of machine learning, say pack learning, in which I can prove something, and then also prove the security properties that I wanted on top of that. But as you can guess from my tone, I want to argue that both of these roads are very bad, so you don't want to do either of these things. Right? Because the utility we need, it is not useful if we cannot do anything with it. And the security, as we said, basing it empirically is problematic. Okay, so what can we do about that? So what I will try to convince you of is that we do have, by now, this large arsenal of tools we developed in cryptography because of all of those hard-learned lessons from before. And we can try to apply both those tools and ideas from those fields in machine learning to try and get those formal security guarantees while not hurting the utility. And one tool that I will focus on in this talk is a notion called indistinguishability or computational indistinguishability. This is something that we use a lot in cryptography, in some fields within complexity theory. And I will show how this thing helps us avoid defining those things that we couldn't really define. So let me try to sketch a general recipe, and afterwards I will go deeper and mention more specific examples. Okay, so what is going to be our general recipe? We are going to take a model that we are not going to assume anything about. So this is a good model that was tested just for utility. And now we are going to construct a new model that probably has a security property that we care about. And we would want to argue that the utility is preserved, that the utility is just as good. And how are we going to do that? We will do that by proving that the two models are computationally indistinguishable. So what does that mean exactly? So this is going to mean that whichever polynomial time algorithm, any efficient algorithm that I have, that I would allow it to interact with both the original model and the new model that has the security property, will not be able to distinguish them. Meaning that if I have a polynomial time algorithm that managed to distinguish between the original model and the transformed model, the same algorithm could also be used to, say, factor integers or break cryptographic assumptions in some other way. And this would mean in particular that any definition of utility I might have is also preserved. Why? Because whichever definition I have for quality or utility and so on is not something that I need more than polynomial time to notice, right? If I have something that degrades quality, but I need to spend exponential time to see it degrading the quality, I will not view this as a reasonable notion of quality. In particular, this also means that any benchmark would behave exactly the same on the two models, the runtime would behave the same, and so on. So I want them to be completely indistinguishable to any efficient distinguishing attempt. And I am going to give a list of examples of where you can actually get this type of definition and what it was useful for. So one example that I will talk about for slightly longer than the others is watermarking language models, or watermarking the outputs of language models. This was then adapted by Google for a stint ID. I will also say why they wanted to adapt this, because as Sela and other people mentioned before, it is usually hard to convince companies to adapt things that are meant to help security. I will also talk about things that are from more of the negative side. I will talk about backdoors in machine learning networks that can also be provably undetectable. And I will also talk about things related to steganography and some implications on AI safety. Okay, so a problem that people care about for various reasons is the problem of detecting whether or not a text is AI generated. Or for that purpose, it could have been anything else besides a text. It could be a code, it could be an image, and so on. But detecting whether or not some content was AI generated, there are various reasons you can think of in terms of finding if something is an influence campaign, if something is a bot or a human, if a student used the AI to do their homework. But the reason that convinced also companies to care about this is that it turned out that it is a very bad idea to train your models on AI-generated content. So this also gave some internal reason for the AI companies to be able to filter out data that they generated with their previous models, which is now swamping the internet, when they are collecting the data to train their next generation model on. And what did people try to do in the beginning? People just tried to train detectors. Train another model that tries to distinguish between natural text and AI-generated text. But this is, in a strong sense, doomed to fail. Why is this doomed to fail? First of all, you cannot really trust it. If I say something like, I think that this person used AI and I'm 50% sure, or 80% sure, or even 95% sure, this is not enough to actually do anything about it in many scenarios. But also because this is exactly the task that machine learning is very good with. I have like one parameter and I want to optimize this parameter. This parameter is how much the detector thinks that this looks AI generated. It is usually very easy to train models to break out of that one extra parameter. So what is a reasonable approach? A reasonable approach is to plant a watermark intentionally, to change something in the text I am generating such that I will be able to say that this was generated by my model and was not generated by nature. And many, many people try to do that. And here is like some prominent example of how you could do something like that. So something that appears as a very nice idea is to just randomly split the dictionary, say, into halves, a half of words that I like and half of words that I don't like. and give some extra incentive for the model to output words that I like, words from this list of good words. And then I should be able to detect it because natural text would have roughly half good words, half bad words, but text that was generated with this incentive would contain many of the good words. So it would be detectable. What is the problem with doing something like that and doing nearly any intentional watermark planting that you can think of? The problem is that I am changing the distribution. I am modifying the outputs of my model, meaning that possibly I can make my language model much worse. And this is something, again, as Sela said, that the companies are afraid of much more than they care about security or any notions of safety. So if this would make my model worse than the models of the competitors, then this is not a price I'm willing to pay. So the question is, could we still do that, plant a watermark that we can detect, but remain just as good? And I started this talk by spoiling how we are going to do something like that, right? So what would we want to do? We would want to take whichever language model we started from, create or transform it into an LLM that produces those verifiable watermarks, such that the original LLM and this LLM that produces watermarks are indistinguishable from each other. Yeah, meaning, for example, that the quality could not be affected. But there is something weird about this statement. Something that is weird about this statement is that I am able to detect the watermark. So there is a difference between the two models. And this requires us to add a secret key into this definition, meaning that I need some secret key to be able to detect the watermark, but without it, the two models are indistinguishable. Meaning that for any definition of quality that doesn't know the secret key, there is no difference between the two models, but if you have the secret key, then you are able to detect what was an output of it and what was not an output of it. Okay, good. And all we would need to know about an LLM for this to work is that an LLM is not just a box that gets a prompt and outputs whichever response the LLM wants to give me, but it actually samples this response out of a distribution. So the way language models work is that they have the model itself, say the weights or whatever defines the model, they have the prompt, the question that was asked, and then they sample a response out of a certain distribution that the model and the prompt define. So the general idea to do something like I mentioned is going to be very simple. So implementing it is a bit harder, but the general idea is just the following. We are going to run the language model as we are supposed to, but instead of using real randomness, we are going to use pseudo-randomness, meaning that we are going to use something that is indistinguishable from an actual sequence of random bits, but it is actually seeded with some short seed and our secret key and so on. So in practice, anytime you use randomness, you are actually using pseudo-randomness. But here we would want to use a pseudo-randomness that is taking our secret key into account somehow. And then what we can hope for is that because we didn't use randomness, but we use this more restricted form of pseudo-randomness, we would be able to detect it because it lowers the entropy of what can be given as a response. What is the problem? What is the non-trivial part about what I'm saying? Is that we want to do it in a way that we can actually detect efficiently afterwards. Right? And what is the problem with being able to detect it? The problem is that I'm not seeing the pseudo-randomness. I'm seeing what was sampled using this pseudo-randomness. And even worse than that, I don't even know what the distribution was. Why don't I know what the distribution was? Because even if I would assume that I know the model, and I wouldn't need to assume that in the end, but even if I would assume that I know the model, I certainly don't know the prompt when I'm seeing AI-generated text in nature. Meaning that I cannot recover what the distribution that the response was sampled from is. So even if I add a guess for what the randomness should be, I would not be able to check that I saw the same thing. All right, so I'm not going to dive into technical details. I will just give you one slide on some intuition about why you can still do that. The way you could still do that is by introducing a sampling process that still, if you would feed it with standard randomness, with real randomness, it would sample according exactly to the right distribution. But this sampling process would make sure that there is a correlation between the output bits, the actual text we are seeing, and the randomness. Meaning that if the sequence of randomness started with a 0, say, then there is a slightly larger chance that the first bit in the text of the response would also be a 0. So we are creating some correlation between the output itself and the randomness that was used to generate it. And then we also need to generate a certain type of pseudo-randomness that with the key can be recognized from something that is correlated with the pseudo-randomness that we used. But this hopefully gives some intuition for why this could be possible. And as I said, this turns out to both work and even be very practical. Why is it very practical? Because we are not actually changing anything about the training process. We are not actually changing too much about the sampling process. The only thing we are changing is my pseudo-random number generator, essentially. So like this change would not be that significant. So all I'm changing is that instead of using, I don't know, like the Python's pseudo-random number generator, I'm using a slightly more complicated one that also gets fed my key. But it wouldn't cost me that much time, and this is why it could also be implemented. Okay. Going a step further from watermarking, we can ask ourselves if a watermark just allowed me to say if something was an output of my model or not, could I actually encode more information than that? This is something we call steganography. And it turned out that we can also do that. Also do that in what sense? In the same sense as before. Without a secret key, the original model and the new model would be indistinguishable from each other, but with the secret key, I can recover arbitrary information that was hidden during inference. So what does that mean? This means that the model can choose to hide, or whoever is running or inferring from the model can choose to hide any arbitrary information in the output that will be retrievable with a secret key, but it would not be detectable by any algorithm, any polynomial time algorithm that doesn't have that secret key. So here is an example. So again, this is easy to implement, so we could also implement this. We did not optimize for exactly the correct entropy you can get, only up to constants. But it shows that, for example, using standard models, this is from a few years back, so this is Llama 2, you can ask the model to produce, say, an email, and this email would encode the username of who used the model at this point. And with the secret key, we'll be able, from this response that was sampled according to the correct distribution of Llama 2, you would be able to infer from this email using the secret key the name of the person who used the model. All right, so what are the implications of something like that? The implications of something like that is that even if I have secure computation and even if I have a completely offline run model, still the model could leak whatever information it wants. Right? Even if OpenAI, I paid them a lot and they gave me yes. That's a very good question. Yes. So I'll not say much about robustness. With the standard watermarks, we can add robustness to certain edits or a certain degree of edits. With steganography, it gets harder because you need to, the more robustness you would want, the less entropy you would be able to encode. But that's a very good question. Yes. Okay, so this means, as I said, that, for example, even a fully offline model can leak information. If I run an OpenAI model on my own computer and OpenAI wants it to leak to them, say, my credit card information or any internal data, then the model can leak in its responses, whichever data it ever saw. It means that agents can communicate with each other secretly, or chain of thought is not really monitorable. Why? Because agents can use steganography to encode whatever they want into text they are producing, whether it is in the COT or in responses from one to another in a way that would be provably undetectable. So any attempt to moderate COT or any attempt to moderate the interaction between agents would not be able to find this type of secret communications. And another thing that this means is that if OpenAI or Anthropic or anyone else chooses to put some backdoor or some malicious component inside their model, then the trigger for making this run can be completely hidden. Because it could be that the text I'm I am giving to the model that would trigger the backdoor as under steganography, whichever actual command I wanted to run. And this would not be monitorable by any attempt to filter the prompts or anything else. Again, because this is provably undetectable. Okay, the last thing I wanted to mention, focusing on this point of backdoors, is another result that is more of the negative type of result, which is that with some asterisk, any neural network, we can take it, plant a backdoor in it. I will soon say what do I mean by that, in a way that is again undetectable. What do I mean by undetectable now? That if I give you the original model and I give you the model in which I planted the backdoor, the no polynomial time algorithm will be able to tell you which is which. No polynomial time algorithm will be able to say that this network has a backdoor. What is a backdoor for me? A backdoor for me is the ability to take any input and efficiently change it a tiny bit to get whichever output I want. So a backdoor is this pseudo access that I am keeping for myself. I am keeping to myself the ability to take any input, any output, and the secret key, and change the input by a little bit to either flip the output or get a different output of my choice. And what we show is that you can do this thing, again, at least in the Q&A I can go further about the definitions, but in a very strong sense, you can do that in a way that is provably undetectable. And what does that mean? This means that if I just get a complete model that somebody else trained, and I want to evaluate its integrity in hindsight, I cannot do that. There is no algorithm, no interpretability effort, nothing that will be able to look at a model and say if it has a backdoor or not. Why? Because we can plant a backdoor in a way that is provably undetectable by any efficient algorithm. Right, so this is bad news for trying to look at a model, run some evaluations, run some benchmarks, run some interpretability, and say if it is okay or not okay. You cannot do that. But on the bright side, it does point out which things we should pursue, and people are pursuing those things. People even talked about them today. So there are ways to do mitigation for this type of bad behavior, even without being able to just assess or detect it, right? For example, people can talk about mitigating without detecting. You can talk about wrapping something around my model such that I will be guaranteed that this wrapped thing is safe, regardless of whether or not the original thing had a backdoor in it. So we don't rule this out because it doesn't require detection. You could think about providing certificates, telling people what did they do during the training process. If I can give you some proof that I ran maybe the correct algorithm on the correct data, then this is a good thing, right? Because then I don't only give you the complete model, I give you some proof that it was made correctly. You can also think of things like real-time, inference time detection. Because when somebody is using the backdoor, if the backdoor is doing something bad, then they cannot hide it. They want to do something bad. So at this point, I could be able to detect it. Okay, let me wrap up with some takeaways. The main takeaway, which is not a new takeaway, but this is something that anyone working on security should be confronted by, is that security and trust should not only be based empirically in your own company's basement. You cannot run tests and say it looks safe, so let's go on with it. But then on the bright side, we do have decades of research focusing exactly on how to base security more formally. This comes from, again, everything related to cryptography, encryption, trust in the internet, and so on. So we should use those tools that we have developed for so many years. And finally, another message that I'm hoping that I managed to convey is that sometimes a stronger sounding notion is easier to prove because it is more rigorously defined. So say, it still looks good, bro, in the sense of an LLM still looks like it works okay, might sound like a much easier objective than making two models indistinguishable, but it is not well defined. So it is much harder to prove than the stronger notion that has a rigorous definition. Okay, I will finish here. Thank you very much, and I will have a Q&A session at 4:30.